Okay, so yesterday we talked about scalar and vector quantities. Now, hopefully, y'all got a good understanding about what scalars and vectors are, and you completed the exercises that I had you do on PhET and on Google Forms. And if you have any questions or something just didn't stick with you, let me know. Send me an email or drop a comment or a private message in a Google Classroom, and we'll make sure that we're not continuing this unit lost on what vectors are. Okay, because they're going to come up today as well in this lesson. Okay, so we talked about scalars and vectors. We said the scalar has a magnitude, but no direction, and a vector quantity has a magnitude and a direction. And we said that you can add or subtract. They can be graphical or analytical. Let's get through here. Touch on the high points we talked about yesterday. We talked about the tip-to-tail method of adding vectors. And we said that the resultant vector is the vector sum of those. We also did it with multiple vectors. We did vector subtraction. And it was basically the same thing as addition, but the one you're subtracting, you turn it in the opposite direction and then follow the tip-to-tail method. We talked about equilibrance, which is a vector that is you can think of it as equal and opposite of the resultant vector after adding two other vectors together to bring a system in equilibrium. You'll see today why it's important, or one of the reasons why understanding vectors are important. Okay. So we're about to jump into our kinematics and really start talking about motion, and hopefully by the next two lessons we'll dive into speed, velocity, acceleration, all those things. Okay, so kinematics, what is it? Kinematics is the study of motion without reference to mass or force. Okay, without reference to mass or force. For the next 2 weeks, we'll be studying how things move in one dimension, which means only in one direction at a time. We'll get to two dimension later in the year. There are three main subtopics we're going to discuss: position, velocity, and acceleration. For this lesson, we're going to focus on position, which is where you are and how far you went. So position can be described in two ways: with distance or something called displacement. The first thing we're going to of those two that we're going to discuss is distance. So what is distance? Distance is a scalar quantity. There's only a magnitude, contrary to displacement, which we'll learn is a vector quantity. There's only a magnitude, meaning if you remember your definitions, and there's not a direction assigned to it. For example, the odometer on a car measures how far the car goes. And it only counts up regardless of which direction you're driving. So in your car, your odometer, that is total distance traveled, and that is a scalar quantity. And we should know that though, right? Because when we're driving in a car, we go 100 different directions. We're always changing directions, but the odometer keeps going up, and you get a total different distance traveled on the car. So that's an example of a scalar quantity in reference to distance. So total distance, by definition, is how far you go, regardless of which direction you travel. Okay, so then we have a check for understanding. If you go 4 miles north, then 3 miles east, then 4 miles south, What was the total distance you traveled? Let's see, I'll go to my whiteboard, I'll draw this out, and we'll see what this looks like. Okay, so our check for understanding says we're going to go 3 miles east, 4 miles north, and 4 miles south. So I'm going to draw that out. And just imagine you're in a car, and we're going on a street, and we're going 3 miles to the east direction. Now, if it'll help you, I'll go ahead and draw our cardinal directions up here. So we know. Y'all are expected to know this, okay? What the coordinate direction, what our cardinal directions are. Okay, so we went 3 miles in the east direction. Okay, that's the very first thing we did. Next, it says we turn and go north for 4 miles. I'm going to draw this one a little longer. We went 4 miles north. Black. 4 miles north, and then we turn around and come back south another 4 miles. Four miles south. Okay, so we're looking for total distance traveled. So in order to do that, we need to add as if we were a car, as if your car was, as if your odometer in your car was reading this trip, you would add 3 plus 4 plus 4 again, because we went this way, come up north, turn around, come back south. So total distance, if we were to stretch this out in one straight line, would be 11 miles, because 3 plus 4 is 7, 7 plus 4 is 11. Now, we said that distance is a scalar quantity. Okay, it's a scalar quantity. So when we record our answer, we don't need a direction. We just need a magnitude with units. While I have you here and we're talking about it, in physics, if you record your answer, always include your units. And we'll get into that later. But always include your units, okay? So since this is scalar, we just have a magnitude plus whatever unit we're traveling, right? If this was kilometers, we would say 11 kilometers. But we're using miles, so we're going to say 11 miles. Okay, so the next thing we're going to talk about is displacement. The definition of displacement is as follows. The difference between where you ended up and where you started. You only care about the end and beginning points. It doesn't matter where you went in between. That's unlike distance. It doesn't matter where you went in between. It just matters on where you began and where you ended. That's your total displacement. So what we're going to do now is take the same scenario, but instead we're going to find its displacement. So we're going to, or I guess it's not the same scenario. We're going to take another scenario and we're going to find its displacement. So on this one, we're going to go 4 miles north, 3 miles east, then 4 miles south. So I'm going to scoot over to my whiteboard and we'll see what this looks like. Okay, so here we are back at my whiteboard. The problem says to find the displacement, we'll write it out so we'll remember. Find the displacement if you go 4 miles north, three miles east, then 4 miles south. Okay, we need to find its displacement. So I'm gonna do this again, kind of like we did last time. So I'm gonna make a starting point. All right, here's my starting point right here. That's where we're starting. So we're gonna go 4 miles north. 4 miles north. I'm gonna indicate that so I don't get lost later. And I'm gonna put arrows to indicate which way I was traveling. Next, we went 3 miles east. So naturally, I would make a little smaller arrow and then label it 3 miles east. Then I turned and went south 4 miles. Then I went 4 miles south. So before I walk you through how to find displacement, I want you to notice that his distance traveled is equal to 4 plus 3 plus 4, 11 miles. Right? It's a very similar scenario to our last problem. He traveled 11 miles. But remember the definition of displacement. Displacement looks at only where you began and where you ended. So where I began and where I ended, which is right here. Okay, let's play with the stars a little bit. So what does that look like then? If we started here and ended here, our displacement vector, remember vectors, would be this here. And it would be a total displacement of 3 miles, the east direction. Okay, that's our displacement vector. Okay, and in physics, what we're going to do is we're going to make sure we box our answer. And there you have it. Our total displacement is 3 miles east because we started here and ended up here. So as you can see, he only actually went 3 miles from his starting point. And that's the difference between distance and displacement. See, distance was 11, displacement was 3 miles. Now remember what we said, displacement is a velocity. Displacement is a vector quantity. Okay, displacement is a vector. So remember, vectors have a magnitude and a direction. The magnitude here would be 3, and my direction would be east. So we have a magnitude and direction. And this blue arrow here would be my displacement vector. And of course, we have to include units. Like we done in the last problem, always include your units, 3 miles east. All right, so let's go back to our presentation and we'll see what else we have to learn. Okay, here we are. Look at the bottom paragraph. It says displacement is a vector. It has a magnitude but also a direction, as we saw in our example problem. With vectors, a negative sign doesn't mean less. It indicates a direction. That goes back to our lesson 2 days ago, remember? A negative sign doesn't mean less. A negative sign is in, when you're talking about vectors, is a direction convention. Remember what we said? We said that up and to the right is positive, and down and to the left is negative. That's the typical direction convention. Now, depending on your frame of reference, that could be different, but for the purpose of this course, that's what we're going to consider our direction convention. Okay, moving on. Here's our definition again. Okay, I put it up here at the top, so we'll have it when we do this next problem. So we're going to do one more. Check for understanding. If an object A has a displacement of 5 meters and object B has a displacement of negative 7 meters, which is farther away from the starting point? Remember, when we look at this problem, we have to think about our direction conventions and the fact that this negative sign does not mean less. It does not mean less. An object, or excuse me, a vector with a negative could have a greater magnitude than one of positive value. And until we understand that, vectors and direction conventions are not going to be intuitive for you. So let's see what this looks like. I want to draw it out again. All right, so let's consider our problem from our presentation. It says we have two objects with the same starting point. I indicated it here with a star to show where they're both starting from. And it said one has a displacement of positive 5 meters. And I'm going to indicate my positive direction up here. This was what I would always do when I worked physics problems, especially Newtonian physics, when I'm dealing with forces, force diagrams and stuff. I would write this at the top for people that were reading my work and myself to indicate that to up and right is the positive direction, okay? And we're going to write that for our own benefit here. So it went 5 meters this way. And the next one, it said, I'm going to do this in a different color. He said to go negative 7 meters in the negative direction. Negative 7 meters. So we look at these vectors and it asks which one is further away from the starting point. Now keep in mind, we're not looking at the sign of the vector. we're looking at its magnitude. Right? Its magnitude is illustrated by how long this vector is. And remember from yesterday's lesson, we want to try to draw those to scale as much as we can. So to answer our problem, the -7 magnitude vector, or the 7 magnitude vector, is longer. Or to answer our question, the vector that's -7 meters from the starting point has a greater magnitude and is further away. And the purpose of this question is for you to understand that negative and positive conventions when dealing with vector directions is only to indicate direction from a reference point. In this case, our reference point was right here at the start, or our starting point. Okay. So the next question asks, what could you use to show the location of a person over a given period of time? This is a question to lead us into our next lesson that we'll talk about the following day. What could you use to show the location of a person over a given period of time? So I want you to think about that after you watch this video and you complete your assignment. Think about what you can use, and that you also use in math class, to show the location of a person over time. When you come back the next day, this is going to be your warm-up question. Your warm-up question is going to be your answer to this question here at the bottom of this slide. For those of you that are coming to see me on Monday and coming to school, words cannot describe how excited I am to see your faces. It's been a while. I really look forward to it. You guys stay safe, and I can't wait to see you then.